This model artifact is larger than the installed video memory. DeepSeek v4 Flash Q3 totals 97.051 GB. The machine has 3 RTX 3090s and 1 RTX 4090 for about 96 GB of installed VRAM. The model still runs, but roughly 9.5 GB of mainly mixture of experts weights remain on the CPU host. The real question is not whether a server can start. It is whether the larger Quant can finish agent work often enough and quickly enough to justify crossing that memory boundary. Offload speed is a property of the whole host path, not the Quant file alone. This machine uses a Ryzen 5 3500, 6 cores, 6 threads, 1 NUMA node, and 16 MB of L3 cache. llama.cpp used 6 CPU threads. System memory is 416 GB single rank, unbuffered DDR4 modules, populated across all 4 slots. The DIMMs mix crucial and A data, and DMI reports a configured speed of 2666 megatransfers per second. That setting is not a measured stream memory bandwidth result. During the Q3 run, the 3 3090 links were observed at Gen 2 by 2, Gen 2 by 1, and Gen 2 by 1, while the 4090 used Gen 3 by 16. Peer-to-peer GPU access was not used. The 3 candidates were IQ1M at 80.933 GB, IQ2M at 84.682, and IQ3 XXS at 97.051. IQ1 and IQ2 used the controlled GPU memory plan. Q3 required a separately labeled best practical configuration and partial CPU host placement. The task contract is shared, but the deployment settings are not identical. The first Q3 fit pushed 23 tensors, about 15,638 MB by the placement log, into CUDA host memory. A short generation smoke test reached only 5.53 tokens per second. I reduced batch size from 2048 to 512, reduced micro batch from 512 to 256, quantized the KV cache to Q80, and lowered the fit margin to 512 MB per GPU. The host set fell to 14 tensors and 9,734 MB. The smoke result rose to 7.31 tokens per second. An aggressive setting used still more VRAM, but moved no additional expert tensors and improved that one smoke sample by only 1.84%. I kept the safer middle setting. The selected 5-repeat Q3 run completed without an out-of-memory failure. Aggregate observed GPU use peaked at 93,531 MB. The lowest recorded available system memory was about 58.64 GB, and the benchmark process reached about 2.39 MB of VM swap. Small system swap input and output deltas were also recorded. None of that makes the deployment fully GPU resident. The verbose placement log identifies 14 host tensors, mainly mixture of experts weights in layers 38 through 42. The graph shows observed system state, not model-only allocation, and the log, not the GPU total, is the evidence for tensor placement. Each headline benchmark number is the median of 5 repeats. At a depth of 8,192 tokens, prompt processing for 4,096 input tokens reached 220.01 tokens per second for IQ1, 211.87 for IQ2, and 142.89 for the offloaded Q3 deployment. Generations separated more sharply. IQ1 reached 33.28 tokens per second, IQ2 24.44, and Q3 14.34. These are Llama bench throughput measurements. They are not first token latency, answer quality, or the time required to complete a tool-using job. To test useful work, every shortlisted deployment received the same 3 repository tasks, repeated 3 times with fixed seeds. Inventory planning required stock arithmetic, reorder thresholds, pack rounding, validation, and input immutability. Event rollup required ordering, revenue aggregation, conversion rate rounding, and malformed input handling. Dependency batching required parallel deployment frontiers, deterministic ordering, cycle detection, and unknown dependency checks. The agent could read files, write only solution.py, and run the visible tests. After each run, an independent process executed hidden tests the model never saw. A run counted as successful only if the runtime stayed healthy, the agent reached an answer. Both test suites passed, and the fixture remained unchanged. Context was 8K, reasoning was high, concurrency was 1, and each response was capped at 3,000 tokens. This is not an original screen recording. It is a chronological replay built from saved tool events, file states, and test results. In Q3 dependency batches repetition 1, the agent read the task and the broken implementation, guessed a test file name that did not exist, ran the available visible tests, then inspected their contract. It rewrote the algorithm to validate names and dependencies, build the dependency graph, and emit parallel batches in deterministic order. The visible tests turned green. The independent hidden tests also passed. The full job took about 338.7 seconds. That success matters. Q3 was not simply broken. It could still complete a multi-step repository task. The question is whether the larger deployment improved reliability enough to pay for its delay. The failures were operationally different. In another Q3 dependency run, the model repeatedly reversed the dependency direction. It edited the file several times, but the decisive logic remained wrong. After 12 turns and about 297 seconds, both visible and hidden tests were still read. A Q3 inventory run failed earlier in the toolpath. A long write file response reached the 3,000 token cap. Its tool call arguments were malformed or truncated, and Llama server returned HTTP 500 after retry. A IQ2 showed a third pattern. One inventory solution passed every visible test, but accepted Boolean true as an integer. The hidden suite rejected it. These replays expose more than a 6 out of 9 or 7 out of 9 score. They show whether the agent misunderstood logic, broke its tool call, or overfit the examples it could see. Across the small 9-run samples, IQ1 completed 6 jobs, IQ2 7 and Q3 6. IQ1 came from an earlier server session, so this is a deployment comparison, not one synchronized server run. The surprising result was time. IQ1 had the fastest isolated decode, yet its median end-to-end job took 144.96 seconds. IQ2 generated more slowly in Llama Bench, but finished jobs in a median 61.84 seconds. Its median completion was shorter, 2,065 tokens versus 3,145 for IQ1. Q3 used a median 3,214 completion tokens and took 230.42 seconds. Its median elapsed time was about 3.73 times IQ2's, without an observed increase in successful runs. Token speed alone did not predict agent speed. For this machine and this small coding workload, IQ2 was the practical balance. IQ1 remains the choice when isolated decode speed and more memory headroom matter most. The Q3 deployment did run, completed 6 of 9 jobs, and avoided an out-of-memory failure. But it kept roughly 9.5 gigabytes of mainly mixture of experts' weights on the host, generated more slowly, and did not increase the number of successful runs in this sample. That is not a universal quantization ranking, and it is not proof that larger quants are lower quality. It is a scoped deployment decision. Before choosing the biggest artifact that can be forced to load, measure where its tensors land, how long its trajectories become, and whether the agent actually finishes more work.